In this lesson, we will talk about a polar form for a complex number. Up to this point, we have been talking about and working with the rectangular form for a complex number, known as z equals a plus bi. However, since we have now also established how to find both the modulus and the argument for a complex number, which is very similar to the radius and theta, or the angle measure, for a polar value, we should also be able to represent a complex number in polar form. The way that we're going to go about that is we're going to use some equations that we have developed in the past that connected values of x and y to r and theta. The equations that we've used before was x equals r times cosine of theta, as well as y equals r times sine of theta. These are equations that we use to try to connect the rectangular and polar coordinate system. We should be able to do the same thing to connect rectangular representations for complex numbers and polar representations of complex numbers. The way we're going to do that is we consider and think about how the real component of the complex number a in the above representation, we consider that and align it along the x-axis. So we can think about x very similar to a here. Likewise, b, the imaginary part of the complex number, we aligned very similar to the y-axis, so we can connect that with b. We have also said that the modulus can also be represented as r. The modulus is the distance from the pole in the complex polar plane, so we can just call that modulus of z instead of r times cosine of theta, and modulus of z times sine of theta. Well, now I can take that rectangular form of z equals a plus bi, and I can replace both a and b with these two equations. So that would look like modulus of z times cosine of theta plus modulus of z times sine of theta times I. Now that's all well and good, however we can try to simplify this a little bit. For one, I see that both of these terms have a modulus of z, so I can factor that out of both terms and rewrite this as the modulus of z times the quantity cosine of theta plus I times sine of theta. I chose to reorder I to be in front of sine of theta here. This would be the complex polar representation for a complex number. Modulus of z times the quantity cosine of theta plus I times sine of theta. This is one way to represent that in polar form. However, you may notice that it's a little bit lengthy and it takes up quite a bit of space, so we do have a shorthand version of this. Note, though, that the shorthand version that I'm about to demonstrate is more of an informal way of writing this. It's not a formal trigonometric function, but it's one that just is a shorter way to write it because we are going to be using this expression quite a lot. The expression that we'll use to simplify this is, if you noticed in my equation at the top here, I have c, I, and s for cosine, I, and sine in a different color. The reason for that is because that is where I'm going to get this simplification. We were always going to have the expression cosine plus I times sine, and both trig functions are of the same angle measure. So we'll reduce that down to demonstrate cosine plus I sine just with three letters of c, I, and s. So this is where we get the form modulus of z times cis of the angle measure theta. Again, this phrase cis, this is just shorthand for this longer expression, cosine of theta plus I times sine of theta, and it is just informal. Very often, it is going to be the case that we will write it in this format for some simplification of calculations later on. However, if we do need to convert back and forth, it is very good to understand how to expand CIS of theta into the expression cosine of theta plus I times sine of theta.